takes negative 69. If you had one step, if you basically, that works pretty well. If you had one reaction that went A all the way to D, how much energy would that take?
20 plus 20.
Nope.
What?
Oh, did you already do the math?
Yeah.
Okay, plus 20?
Nope.
Plus 20, thank you. I thought you were throwing out numbers again. Then I looked at it and I'm like, oh yeah, it actually is plus 20. So yeah.
Wait, so you just add and then subtract?
A to D. Yeah, so if your reaction takes 3 steps. Oh yeah, okay. If your reaction takes 3 steps, and you come up with a new system that can do it all in 1 step, as long as you start in the same place, in this case A, and end in the same place, in this case D, the actual amount of energy will be the same. It's kind of like if you gave somebody a directions to your house, and you said, okay, go down this block, go down this block, go down this block, turn left, go down this block, go down this block, turn right. You could basically say, or you could just do it in one trip. You don't have to stop every block. You do all in one trip. The amount of energy is going to be the same.
Now you need to stop at 7-Eleven, get me a drink, and then come here.
Get you a giant gulp, an Uber gulp.
Super gulp.
Super gulp. The super Uber gulp. It's basically a backpack that you just fill up with sort of. Okay, give me a thumbs up if that makes sense. We've got to change gears. Okay, cool, that's Hess's law. All right, Hess's law can be summed up just like this. The enthalpy of the products minus the enthalpy of the reactants is the enthalpy of reaction. This is where we're going to end today. Okay, so enthalpy of products minus enthalpy of reactants, and that crazy looking E is the Greek letter sigma. It means all of them. Okay. So all of the products minus all the reactants gives you the enthalpy of reaction. We're going to go into greater detail about this next week, but for now, just realize Hess's law, extremely valuable, products minus reactants.
Wait, what is it?
What if I invent the time machine and then I claim this stress?
Then we call it Cowley's law.
Wait, then who would have invented it?
Yeah, Cowley would. It would be like Cowley's law. But then it would be like because then it would create a time loop.
Yeah. Wait, so is it?
And the time rate would come bother you.
But like, if you go back.
All right.
It's like panic.
All right,
So what
so
does it equal?
it equals the enthalpy of reaction. So in this case, my quick little example, the products have an enthalpy of negative 560, and the reactants have an energy of negative 240. What would be the enthalpy of reaction? Nope.
It'd be 320. Negative 320.
Negative 320. So negative 560 minus negative 240 tells you the reaction would have an enthalpy value of negative 320. Exothermic or endothermic?
Exothermic.
Exothermic. And lastly, what's more stable? The reactants up here or the products down here? The products. Remember, the universe prefers low energy states. So the products are more stable. The reaction barrier or the reaction path, it would look like that. Only it wouldn't go backwards. It would look more like that.
Went backwards.
Which I'm backwards again? Yeah, well. You come up and try. All right, questions? There's no questions? We're going to move on. All right, moving on. So in the next 17 minutes, you need to do the pre-lab for tomorrow's lab.